Alright, this is study session question number 1 for circular motion. The frequency of rotation of a space station is 2 revolutions per minute. If the radius of the space station is 100 meters, what does a bathroom scale read when a 70 kilogram astronaut weighs herself? So here we have the astronaut. Radius is right there. Okay, let's take a little bit of time to remember what our formulas are. So remember that centripetal force is equal to the net force, which is equal to mv squared divided by r. Okay. Also remember that centripetal acceleration is equal to v squared divided by r, and then remember that v, if it's a full circle, is 2 pi r over t. Okay, so what we're looking for is the force on this. Like, what would the scale read? Well, if you look, the scale would be the force pushing her into the center of the circle. If that is the force, that is the centripetal force. There should be no other forces acting on her. There's only this force right here, the force pushing her in. So this force is the normal force from the ground, quote unquote, the ground, pushing her in toward the center of the satellite. But since it's the only force acting on her, it is the net force, and so it's also equal to the centripetal force. So if we want to find the normal force, or the force of the scale, or however you want to word it, we need to do this formula right here. Okay, but in order to do that formula, we have her mass. Her mass was equal to 70 kilograms, but we need to find her velocity. So that's what we've got to do next. We've got to find her velocity. Well, if we look, her velocity should be equal to, v is equal to 2 pi r over t, which is all good. We know 2, we know pi, we know r. We do not know t. So how do we calculate t? Well, the period was the frequency was 2 revolutions per minute. So if it was 2 revolutions per minute, so 2 revolutions occurred in 1 minute, or 60 seconds, 1 revolution will occur every 30 seconds. So now we know the time it's going to take, because the time for 1 revolution, 2 pi r would be 1 revolution, that's the circumference, so 2 pi times 100 divided by 30 should give us the velocity. So if we do this, we get 21 meters per second. Okay, and now what we have to do is solve for F net, which will turn out to be the normal force. So the normal force, or the centripetal force in this case, is equal to mv squared divided by r. So the normal force then is equal to 70 times 21 squared divided by 100. And if we do this, we get 308 newtons. Okay, I'm going to go ahead and do study session question number 2 as well, just because that way we don't have to worry about having 8 of these things. So hang on one second. Okay, guys, so in this one, what it says is that we have a 100-gram golf ball on the end of a 2-meter string. It's whirled in a vertical plane with a speed of 8 meters per second. What is the tension in the string when the ball is at the top of the swing, and what is the slowest speed the golf ball can move without going slack? So let's answer that first question first. That seems most logical. At the top of the swing, so this is the general setup, but what we're looking for is at the top of the swing. So I'm going to just kind of draw a dotted line, redraw the golf ball. What are the 2 forces acting on it at this point? Well, you should have the tension pulling down, and then also the force of gravity pulling down. Okay, so we need to make sure we understand that there are 2 forces acting on that. Force of gravity, remember, is mass times 10. So 0.1 times 10 is 1 Newton. Alright? Second thing we got to remember is that the centripetal force does not have anything acting on its own. Something has to be providing the centripetal force. So we have centripetal force equals the net force, which equals the force of gravity plus the tension. Okay? We also know that the centripetal force is equal to mv squared divided by r. So using these two pieces of information here, I'm going to plug in mv squared divided by r equals the force of gravity plus tension. Now I'm going to plug in all of my known numbers. 0.1 times 8 squared divided by 2 equals 1 plus t. And if I do all this, I get 3.2 newtons equals 1 plus t. Subtract the 1 over, and I get the tension is equal to 2.2 newtons. Okay, that's good. So now this is the tension at the top of the string. The way we knew this again was because the force of gravity and the tension were both pulling down. The force of gravity was 1. The net force acting on that object had to be 3.2. So the tension then had to be just 2.2 newtons. All right. For the second part, we want to know what is the minimum speed. What is the minimum speed that the guy could be going up here and not go slack, not let the string go slack? Well, from last time we know that there's the force of gravity acting on it, and there's also the tension acting on it. Well, right before it goes slack, tension will go to 0. So there will be no tension. So what that means is that the centripetal force, or the net force, will be equal to the force of gravity. Okay? So what that means then is that mv squared divided by r will equal mg. Okay, and if you look at this, the reason this is mg, remember, I guess I could just word this instead of mg, I could just say m times 10. Okay, that might make a little more sense to some people. Alright, remember mass times 10 is the force of gravity, so mv squared divided by r is the centripetal force. If you'll look, the m's cancel, so we're left with 10 equals v squared divided by r. R is 2, so we multiply 2 up, we get 20 equals v squared, and the square root of 20 is 4.5. 4.5 meters per second equals the velocity. This is the minimum velocity it could go without falling, and that's because it's right at the instant that tension in the string is 0. Okay, so that is question 1 and 2.